Okay, boom, record. All right, and here's what you can look at that too, so blah, blah, blah. Okay, so how the internet works. First of all, for people that are old like me, the internet is pretty incredible. It allows all sorts of science fiction-y things that weren't in people's heads at all, when I was growing up. So just like my parents grew up in the age when TV was starting to become a thing, and my grandparents grew up even before radio was a thing. And so, every generation has its stuff, right? I mean, for me, TV was the background noise of my life, and I didn't really think much about why it was there or how it got there. For my parents, radio was the background noise of their life, and they didn't think too much about it. And all of you probably grew up with just internet in your house, and it's just something people had. But if you're old enough, it's kind of magical. So, things that were almost unthinkable not too long ago. Number one, instantaneous worldwide communication. You can shoot an email or some kind of message to somebody on the other side of the world in a fraction of a second, which is crazy, right? It wasn't that long ago that if you wanted to communicate with someone on the other side of the world, you had to send them a letter and you put it in airmail and it would take like days or maybe weeks to get to the other side of the world. So that's the way things were. Streaming music and movies, some of you may remember a time before that was a thing. I met my wife in 2007, and at the time she was doing the Netflix thing where you order the DVDs by mail and you watch them and then you send the discs back in the mail. We still have a Step Brothers DVD somewhere in the house from that. Anyway, that was pretty recent, right? And you can remember back when, maybe not Blockbuster in particular, but you can remember when you rented physical media as opposed to just streaming stuff. And social media and groupware, right? This sort of stuff, like when I was a kid, after high school, getting out of high school is a big thing because there was a good chance you weren't seeing any of those people ever again, or maybe not for 20, 40 years down the road if everybody came back to the reunion. So that was kind of it. Right now, anybody you kind of want to be friends with from high school or whenever, you connect with them on Facebook. And we got groupware now. Again, groupware has been around for a little while, but it's really gotten a lot more attention since COVID. Everybody's gotten used to using it. So again, all these things basically almost unthinkable, even 40 years ago. You're like, well, how is that even going to happen? But here we are. And arguably, and in my opinion, humanity's single greatest engineering achievement, right? It requires a tremendous amount of technology to make all this stuff work as well as it does. So, number one, it's always on, never shuts down, right? There's, despite me saying such and such broke the internet, nothing breaks the internet. Of course, your router may vary. Your router may be having a bad day, or, maybe a connection gets broken by some big storm by your house. That's something different. But the internet is still out there. Even if your house isn't working, you can go over to somebody else's house and get on the internet from there. Rarely noticeably congested, right? There's a tremendous amount of excess capacity available for the internet all the time. Now, individual websites, sure, they can get busy. You try to go play Fortnite on the first day of a new season, it's going to be a hassle to get on there, right? It's going to take a while. But the internet as a whole, it's there. You can send your emails, whatever. Stuff doesn't get shut down. It's mostly free once you've paid for your ISP, right? And that's incredible. That enables all sorts of work that wasn't possible not very long ago. Even for applications like video streaming, right? You can go to YouTube and just watch whatever you want as long as you want for free. And finally, mostly uncensored for better or worse, right? There's all sorts of stuff that's available. I don't know. You could have a whole old people conversation about kids today growing up too fast. But number one, it's good that you're able to find stuff that you're looking for, but number two, right? I mean, there's a whole wave of concerns that as a parent or guardian, you have to be concerned about these days. So yeah, anyway, it happens, but it's pretty incredible. All right, so how the internet came about? Well, number one, it was not designed by some government or organizational body that said, we are going to make the internet today, and here is how it will look. Nobody really had a big plan like that. There was some guidance. There were organizations that were trying to advise people, but it wasn't it didn't have an architecture that was designed by a single organization. it is decentralized. There's not a single entity that owns it or controls it. They're just a bunch of different organizations that own chunks of it, and they work together. In fact, the internet actually evolved from isolated networks, with the first one being in 1969. So internet is sort of a contraction for interconnected networks, that if you have a bunch of different networks and you join them together, that forms an internet. And the first one was 4 networks joining together on the west coast of California, 1969. So before then, what happened is that networks existed, but they were pretty isolated. So timeline of computing generally, right? Basically in the 40s, computers are invented. And in the 1950s, businesses are using them for various purposes, right? So 1940s, what they were using computers for, the first actual thing, from what I've read, the first actual usage they did with the big computers that are actually real electronic computers was to compute artillery trajectories, right? So if you had some piece of artillery and you wanted to consider all the ways that the shells might land with such and such elevation and tilt and this and that, they did all those computations, and they cranked it out in massive tables that they could print out and send out as like artillery usage handbooks. So it was a World War II thing. Other things that happened later were like weather prediction, which is obviously important. But by the 50s, they were using it for, much more peaceful purposes like payroll computations, and a lot of big businesses had computers for that. But it was until like the 60s where businesses would have multiple computers, and once you have multiple computers, you're eventually going to figure out some ways that, hey, there's some ways that we could benefit from sharing data, right? So for example, you might have had one computer tracking your production processes, right? And you have other computers out there that are involved in procurement or transaction processing with your business partners, scheduling deliveries, things like that. And you say, gosh, wouldn't it be nice if instead of having to print out these records and sending them over to have Susie do data entry and type all the stuff into, the other system, if we could just put up a cable between these computers and automatically deliver that data, right? And yeah, until you have 2 computers under your roof, networking isn't really a thing. But eventually, you had stuff like that. And then with networks like that, you eventually say, you know what? Our organization has a network, and we produce a lot of information that we could beneficially share or exchange with some other systems network. Let's connect them, right? So in order to have internet, you first have to have multiple computers owned by an organization, and then you have to see a need for networks to be connected, right? Nobody's doing this stuff just for fun. It was actually, for research organizations that they said, gosh, wouldn't it be a lot faster and easier if we could just, transmit our data to each other instead of printing it out and putting it in the mail. Anyway, in those days, there wasn't really a guidebook for how to do this, right? Everybody was doing it for the first time, so they had to figure out, how are we going to do this? We don't really know. Let's come up with some good ideas. So you had a bunch of system engineers figuring out different ways to handle this stuff. And, well, the way it would go is something like this. So I'm going to draw a really shitty map of the U.S. and I guess North America generally, right? So it'll be Canada and a little bit of Mexico. There's Florida or something. I promised it would be crap. And here's the Great Lakes. We're going to do that as a squiggle. Okay. So over here, we're going to draw some networks, right? So suppose there's some here, West Coast, one down there in Texas, Twin Cities over here, and I guess New York. Twin Cities actually used to be a big hub of, computing. Not so much anymore, but once upon a time it was. Okay, so imagine you have all of these different networks, and they're all connected, all right? And I'm going to make this one blue. Okay. So you have a West Coast network and a Midwest East Coast network, and they're doing their own stuff and they're happy. Now, someone at some point says, hey, we're going to connect these 2 networks. Dun, dun, dun. But you have a problem. The red network speaks red, right? Anytime you have a system exchanging information between machines, you have to figure out some language, some standard protocol or process that they use to exchange data. Likewise, the blue network The blue internet speaks blue. They can't understand what red is saying. Red can't understand what blue is saying. So my question to you, when these two networks join, how are they going to decide what to speak? In practice, how do you think that would happen? There's no government board to appeal to. There's no arbitration. You know, you can't just say, the feds say we got to speak blue. So how do you think they decided? Yeah. What's that? Well, in an ideal world, maybe, but the problem with that, let me bring this up to you. So suppose, for purposes of discussion, we can agree that Chinese is a terrible language to use on a typewriter. Okay? Nothing against the Chinese language, but if you've seen a Chinese typewriter, right, it's a lot harder to type stuff on there than it is to type stuff for English language, right? Because of our very limited character set. But suppose this. What's the approximate population of China right now? Did you say 5 billion? Alex, holy shit. Yeah, I would have accepted a billion, though. A billion's fine. 1.4 billion, that's great. So there's a lot of people over there, right? Now, if you go over to China with your wonderful little English language typewriter and you say, gosh, all you Chinese people, you should learn English so that you can use this typewriter, what is China going to respond? What will they say to that? They'll say, no way, man, right? They'll say, you know what, even if it is better, there's 1.4 billion of us. We're not all going to uproot our language so that you can feel a little bit more comfortable with your typewriter, which we admit is very nice, right? It's a very nice way to type, but come on, there's too many of us. Does that make sense? So what happens is mostly that the bigger organization, they'll say, you know what, you've got 10,000 machines, we've got 200 machines. It would be a whole lot of work for you to retool your process to work well, for your 10,000. So yeah, we'll learn to speak yours for a while. So that's what's probably going to happen. If one operation is bigger, they're going to go with that. But to the point of efficiency, it's not an invalid concern. What will probably happen is over time, the blue people might say, you know what, we are going to speak blue because there's so many more of us speaking blue, but there's some things in that red language protocol we really like, and we're going to adopt them for our own process whenever we do the new revision. Okay, so again, in the short term, it tended to be whichever organization was bigger, they kind of went along with that. They all had their hardware and systems geared toward that. It was going to be really expensive for them to change. But one of these other smaller groups had a good point. They say, yeah, you know what? Next time we revise our protocol, we'll include that because that's a great idea. We can do that. Okay? So, and in fact, again, that's pretty much what happened. So when new networks joined a larger group, they naturally adopted whatever protocols were in use because, if you're one network joining a group of 1,000, they're not going to change for you. Okay? And those eventually become established as standards. So standards arise naturally because it doesn't make sense for every different system to set up a custom interface between every different pair of machines. And in the long run, over time, the best elements of all the standards get refined, get recombined, and adopted in a fairly democratic, consensus-based way. What it is they say, you know what, you guys have more stuff than we do. We'll go with that for now, but we have some good points and we hope you include them in the revision going forward. And this is actually fairly analogous to US politics. If you think about, most of us don't get our first choice to vote for president, right? I mean, there are people that run and we like them or don't like them, but hardly anybody gets their first choice. But you get your choice of the options that are up there, right? And that's kind of the way it worked for networking. Is there were not that many, not an infinite range of options, but you got to choose from what was there. That's what they mean. Okay. Now, way back when, the internet was funded basically by defense organizations, right? ARPA, Advanced Research Projects, and the US Department of Defense. So I'm going to ask you this. Has anyone here heard of Al Gore? You heard of Al Gore? Does that name? Who is Al Gore? You, the weatherman? No, that's Al Roker. He was. Well, that's exciting. That's something. Anyway, well, in the 1992 election, all right, he was the vice president. He was the vice presidential candidate and became vice president for a couple cycles there. And in 1992, there was a lot of mockery because some of his words were a little bit taken out of context and, you know, whatever, contorted to say that he said he invented the internet. Okay? And if you ask your parents about that, if you say, did Al Gore really say he invented the internet? They'll probably remember that, you know, if they were in the United States at that time. But he didn't actually say that. What he said is basically he was, you know, very, very important to the development of the internet. And you can debate that. But what is true is he was on one of the government bodies that actually, you know, pushed for this thing to have funding. And so all along he was saying, you know what, the internet is really important. We need to make funding for this. It's going to be a big thing. So he did have his role. All right. So there I am dispelling a long-running urban legend. Anyway, we're going to talk about this. I'm going to lift this picture here. You see what I'm doing? It's weird that this whole setup works slightly differently in different classrooms. Okay. What the hell? Oh, yeah. Use this one. Okay. So I'm going to put this picture in here. Now, the first thing, the backbone, right? I'll do mine in, I guess, red. Backbone is very high capacity, but not needed for ordinary users, right? So you don't connect straight to the backbone out of your house. Instead, what you do is connect to a much smaller local network that runs that cable from one of its you know, data processing facilities to your house, okay? When necessary, that local network will forward data onto a bigger regional network, and when necessary, that regional network will forward data onto one of the organizations that controls the backbone, right? So, for example, suppose you and your somebody else in your house, you're playing Minecraft together, and you've set up a LAN connection, local area network, for all users on one side of the router in your house, right? Which you can do. I've done it with my kids. That request, all those back and forths, they don't need to use the backbone. You can handle all that locally in your house, right? There's no need for the rest of the internet to get involved. But suppose you want to send a communication, suppose you want to involve people down the street in your interactions. Well, then your local network has to get involved, right? Because it's going out of your house through your router over to their router and into their house. Oh, shit. Now, if you want to send something a little further, like maybe to somebody, I don't know, in the Twin Cities, I guess, you got a friend in Minnesota, you want to send them a note, you might go through a regional network, right? You might go through there, you send your information up to the local network says, okay, we can't handle this here, that guy's not on our network, we're going to forward it up to the regional network. The regional network says, oh yeah, we cover that destination address, so we can send it back down through the local network and to him. Finally, if you're in some situation where you want to send a message to the other side of the world, well, that probably has to go through the backbone, right? Something like this. And then through the backbone, all the way through a regional network and a local network on the other side of the world. So this is analogous to how water piping systems work, right? So when they pull water out of the lake and they process it at one of their purification facilities, and then they send it out on these big 24-inch water main pipes that whenever they bust, you know, Lakeshore Drive gets flooded for like half the day. But nobody needs a 24-inch pipe like that hooking up straight to their house, right? Nobody has that much demand for data. Same thing for the backbone. You don't have that high-speed, high-capacity fiber optic cable bolted to the side of your house. I mean, it would be nice for one single user, because if you did, you know, you could download terabytes per second and everything would be super fast. But if everybody had a connection like that, then the real backbone would have to be that much more powerful, right? Would have to have that much higher capacity. So, you know, just like the water pipes, you don't have a 24-inch pipe connecting to your house. You have like a little 1-inch household connection. Same thing, you only get a tiny fraction of what the backbone can carry. Okay, that's the basic architecture there. I'll have a little bit more to say about that. Okay. Now, in the pictures I drew, right, the way it's shown there, it's basically a tree that for any 2 points in the internet, there's exactly one path to get there. But in fact, there's a bunch of redundancy built in. So anytime you see one of those lines, it's actually like a bunch of connections working in parallel. Think of it as like lanes on a highway. If one lane is out of commission, you can still send data over the other lanes. Okay? So again, even if some infrastructure fails, data could still flow, you know, along basically parallel paths and get to where it needs to be. And that's a big part of why the internet is so reliable. It's always on, because there's a lot of redundancy built into the system. If one component fails, another component can take over for it. Okay. Now, ISPs, Internet Service Providers. Ordinary end users like you and me, we do not connect directly to the internet backbone. Instead, you connect through other networks called Internet Service Providers. And there's 3 tiers of ISPs, so we'll do them slightly out of order for reasons that will become clear in a moment. So tier 1, those are the big telecoms, the ones that are household names that used to run lots of ads for cellular, this or that. AT&T, Verizon, Sprint, MCI back when. Tier 1 providers, they own part of the backbone, a significant chunk of backbone, and they can connect to any other network using what are called peering agreements. With peering agreements, they send data for free, as if, you know, they're buddies or peers. Okay, that's what the tier 1 is. And the requirement for being a tier 1 provider is you have to own a certain amount of backbone in some geographical area. Second one, tier 3. So tier 3 providers, those are the so-called last mile providers that connect directly, you know, to your router in your home. Okay, and those again, well, we'll talk about that in a moment. Their defining thing, they only use paid transit to exchange data with other networks. If they want to send data through another network, they got to pay that other network to carry the data for them. Okay? The last one, tier 2. Tier 2s are the bridges between your tier 1 and tier 3 providers. And they rely on a mix of free transit with peering, peering agreements, free data transmission, and then transit agreements with others. So a tier 2 network, if it wants to send data to a tier 3 network, it uses peering for that. It doesn't pay. But if it wants to send it to a tier 1 network, yeah, it has to pay for that. Okay? Now, these strict classifications, they used to be pretty well followed like 20, 25 years ago, but a good example now of how this whole categorization kind of fails is Comcast, right? So Comcast, once upon a time, used to be just tier 3, right? They were only a last mile provider. They only dealt with getting data straight to your house. Now it's officially classified as tier 2, but in fact, it's practically tier 1 in the United States. In almost every case, in almost every part of the United States, it can function as a tier 1 because it does own a big chunk of backbone and it does use peering agreements. But because it doesn't do everywhere, Comcast has voluntarily opted out of being a tier 1 provider in certain oddball parts of the United States, probably Alaska and Hawaii. You know, officially they're classified as tier 2 because they do use a mix of peering and transit agreements. Okay, now we'll bring this back for a moment, back to our paint. Okay. So these guys, these local networks, these are tier 3. Okay. These regional networks, tier 2. And the backbone owners, tier 1. Now we'll talk a little bit about why this works, but the intro to it, you pay your tier 3 provider directly, right? If you have cable with Comcast or internet with them or with Verizon or whoever, right? You pay them every month for it, okay? Now, they have that revenue stream. If they want somebody else to carry data for them, they got to pay them, right? They already have their revenue stream. A big part of the tier 2 revenue stream simply comes from, you know, some fraction of what you pay to your ISP. Same thing for tier 1, right? Tier 2 can handle all of its stuff locally in its region. It's not going to pay anything for that because it provides the infrastructure. But if it wants to use somebody else's superior infrastructure like tier 1, again, tier 2 is getting the money from the tier 3s. Tier 1 expects some money from the tier 2s. That's how that kind of funding works. Okay. And then on the other side, they don't pay. And we'll talk about that in a moment. Like right now. All right. So this is another example. This is the same map, basically, same picture I drew, but just slightly differently presented. But peering versus transit. Okay, so let's pretend we're not talking about technology anymore and pretend we're talking about mailing a letter. Okay, suppose you have a friend in Paris and you want to send him a letter, so you go to buy airmail, right? You go to buy it. What do you pay in the United States? Who gets paid for that airmail stamp? You go to the post office, are you buying a French airmail stamp or a US airmail stamp? Yeah, but isn't that kind of weird? Isn't that because, you know, the letter gets to France and France is going to have to do some work to get in the letter to that guy, right? It's kind of weird that you don't pay France anything. Well, how does that even work? Well, the way it works is that there's an assumption built into the system that if you are sending a letter from the US to France, probably at some point, somebody from France is going to send a letter back to you, and it's all going to balance out, right? That's the logic behind peering agreements. It would be pretty expensive to put in the traffic monitoring equipment to actually track how much data is going through and monitor it and set up systems for all that. It's easier for everybody if they just say, yep, okay, you carry our data, we'll carry yours, and we're not going to worry about tracking it unless there's some seriously huge imbalance, right? So, for example, if France were getting like 20 plane loads of mail from the US every week, but every week there are only like 2 plane loads of mail coming back from France to the US, at some point the postal services of the 2 countries would get together and say, dude, come on, we're carrying all kinds of mail for you. You're not carrying much mail for us. You got to throw us some money or something. And they'd work it out. And that's kind of the way it's supposed to work with these, with these networked operations. So, again, same idea with regular networks. For traffic between tier 1 networks, there's an assumption built in that for every chunk of data going one way, there'll be a roughly equivalent chunk of data coming back the other way. So they don't charge. Okay. Problem though, in real life, see, again, this is one of those things that tended to work pretty well back in the day. But now in a variety of cases, there are massive flow imbalances in certain areas. An easy one is Netflix, right? Netflix, you send some request to Netflix for a movie, it's going to be a very short, simple, compact request, basically like an email, and then Netflix sends you 2 gigs of data, right? So the data flows are definitely overwhelmingly in one direction, right? And Comcast was one of the companies that really took advantage of that trend to optimize their cost structure. So if you have an article there from 2014, it's basically about how Comcast took advantage of the existing situation and these flow imbalances to basically not need to pay too much and really take advantage of these peering agreements. So if you're interested in that, it might make some of this stuff a little bit real. Okay, now for routing traffic across the internet, basically the way it works, you have your device, which is a client device, and you send a request to some other device that's hosting an application. Like say you go to YouTube and say, YouTube, show me a web page or play a video for me, right? You send that kind of request out there. Now, the way that works, first of all of those communications get formatted into what are called packets. Packets are little chunks of data that with a cap of 1.5 kilobytes. Now, the reason why data gets sent in packets, well, would anyone, why, okay. Simple question before we get into what packets are and all that. Why are packets necessary? Suppose you have a message that's a gigabyte of data. Why would it make more sense to send it as packets, as a long series of packets, as opposed to one continuous flow of 1 gigabyte of data? Why would that make more sense? Why do we use packets? What's that? Well, in a sense, packets actually create more traffic because every packet has to have separate information about where the packet's going and what it's from and stuff like that. So packets actually add a little bit more traffic into the network. Anybody? I mean, I know what people are thinking. Well, it's got to be better or faster or more secure or something good, right? Well, there's two things. Number one, it's going to be faster. It's going to be faster to do it that way because even though it does add a little bit more network traffic, the reason why it's faster because there's multiple points on the network where you have to send it to, right? So YouTube sends the message to one router, that router sends it to another router, that router sends it to another router until finally it gets to your house. Now, at every one of those points, if the device is going to forward on that whole big 1 gigabyte slug of data, they have to wait for the whole thing to come in before they can keep resending it, right? I mean, I guess there's a way where they could, send out every byte as it comes in. They could make it work, but they're probably going to wait for the whole thing to come in before they resend it. And so there's going to be long delays at every router. That's one possible. That's potentially workaroundable, though. But the part that isn't workaroundable, if there is a failure in the transmission process somehow, like if one packet for whatever reason fails to go through, then all you have to do is resend that one packet, right? Or send everything after that packet if that stops the stream. But if you send the whole 1 gig file down the network and it gets to the very end and you realize that it's in some way flawed or incomplete, you have to send the whole thing again. There wouldn't be a real mechanism for just sending part of the file. Okay, so, but the other reason why they do, packets are more efficient in the sense they allow multiple users to share the line, right? So we'll talk about that in a moment. But that's kind of outside the scope of the exam. If people are wondering, why do we do it in packets? Well, basically it's more reliable and it's faster and it allows people to share the communication hardware. Okay, now when data gets transmitted across the internet, packets are typically going to get handled by multiple routers on the way, right? It's not like there's a direct connection from your house to YouTube's data center with nothing in between, right? It's going to get routed to one, routed to another, routed to another. And that sequence of network devices between a source and destination is what's called a routing path. So, diagram of one here, the blue dots are all routers, and the pink lines are connections between routers. So if you're trying to send a message from the source in the upper left to the destination in the lower right, you can see it has a lot of different choices about how to go about sending that data, right? It could do one path along the outer left or along the outer right or some alternate path in the middle. There's a lot of choices, right? So question, how do you decide what path to take? Well, there are routing protocols for that. And remember, a protocol is just a standard set of rules for doing something. So there are standard ways to do routing. I should mention at this point, routing protocols were basically what my dissertation was about. This was kind of my thing. I've forgotten most of what I once knew, but once upon a time I knew a bunch of stuff. Yeah, but this is IDS 200, so basically what you need to know is that routing protocols exist, right? But once upon a time, this was kind of my thing. Anyway, since there are typically a lot of different paths, first of all, you have to decide one path, right? And ways that routing protocols might do that is either something like minimizing number of routers involved in the process, right? Like picking the shortest path in terms of going through the fewest blue dots, or it might look at the quality of the individual links between them, the pink lines, right? Whether they're busy or not busy, how you're going to get the data to where it needs to be the fastest. And again, there's a bunch of different routing protocols out there that consider those things, and they're used appropriately in different places. You know, the routing protocol that you might use for a small network is going to be very, very different from what the internet uses as a whole. So whatever, we don't need to worry too much about that. Just that there are different routing protocols, and we will talk a little bit more about that in the YouTube lectures. So Internet traffic also uses HTTP, Hypertext Transport Protocol. What that is transport protocol is the process for basically taking a message, chopping it up into packets, and delivering those packets as a numbered sequence. Okay, so the transport protocol is that, sends all packets of a given message over the same path, right? So TCP/IP is the routing protocol that's generally used for most of the internet, and it does send most of the data. It sends all the packets of a data over a common path. Okay. Now, the internet uses a whole bunch of different components and technologies. So there's different hardware, different network capacity models. So circuit switching is an older one, like for analog phones. If you have a dedicated connection between you and some other user, when you were placing a phone call with those, basically you were renting the price of a copper wire and its maintenance to however far you were going. And that's why long distance calls used to cost a whole bunch. The current model for a lot of things is packet switching. Packet switching makes it very easy for a lot of users to simultaneously share the the telecom hardware. And again, that's what the internet mostly uses. So there's different connection types: wired, wireless, optical, satellite, whatever. Lots of different applications. And of course, wide range of hardware manufacturers and software developers, right? So there's a lot of different technology used on the internet, and it's a fair question to ask, how do you make all this stuff work together? Well, let's talk about this problem scenario. Imagine you have a bunch of different applications, okay, and a bunch of different communication technologies. If you had to design a custom interface for every pair of different communication technologies and different applications, if there aren't too many, it might be okay, right? If there are just these three, that's not too bad. But what it means is every time you add on a new technology, like say cellular, you have to make sure that it has an interface with every application that it needs to work with. Likewise, if you design a new application like Skype, you have to make sure it's compatible with every kind of technology out there. And again, if you're only talking 3 or 4 things, it's not a big deal, but obviously there's way more than 3 or 4 applications out there, right? So this kind of thing is a nightmare. There's a huge amount of work involved. Anytime you introduce a new kind of application or new kind of communications media, you're going to have to do a whole lot of work designing new interfaces for everything else that's out there. And it's just going to get worse with the more applications and technologies you design, right? So it's going to make growth and adoption very, very hard because it's going to be a whole lot of work to design anything new. Even the communication endpoints might be on different communications media, right? So you might have some situation where Ethernet and Wi-Fi somehow need to interact with each other. That's a similar problem. You also have to have different communication interfaces between all of your various hardware technologies as well. So how do we do this? Well, the hint, we use APIs, right? APIs that we talked about last module. Here, these are some slides that I lifted from some source, I've forgotten where, but they call it the magical network abstraction layer. But just think about it, this is an API. Ta-da! And so every technology, every hardware technology has its API, every application, every software technology has its APIs. So anytime you're developing a new application, all you have to do is make sure that it uses the same interface that all of these communication media do, right? As it happens, Wi-Fi was initially developed to use the same sort of packet format that Ethernet used because it was a lot easier to do that. And Bluetooth uses the same, and cellular uses the same. They use the same kind of packet structure so that any device can communicate with these things and use the same communication format. So that means you design an application, you don't need to custom design an interface for every media type. You just need to design it so it produces data in the standard packet format, right? Likewise, for any of those communications media, as long as they accept input and produce output in that same standard packet format, they can communicate with each other, they can communicate with any other application, right? So it's a whole lot less work. Anytime you're designing a new application, you just need to fit it for that one interface, and it makes it really easy to develop and introduce and have your new technologies adopted. Okay. Next thing, the layered network stack. Okay. So anytime you're sending some data from an application to some other machine, it has to go through a whole series of formatting processes before it eventually gets sent out over physical media, right? Before it gets sent out through your wireless card. And we call those different tasks layers. Okay, so your application produces layer, it goes through a bunch of tasks to make sure it's properly formatted to be sent out into the ether, to the internet. These layers are inherently modular. That means they're defined by their input and output formats. So, for example, suppose layer n-1 there, the layer just below n, it expects to receive unformatted application data and it encrypts it somehow, right? It runs it through an encryption algorithm so that it's ready to be transmitted, to be converted into packets by the next step. Well, as far as its interface, it needs to receive application data in any format from the application, kind of doesn't care, and it produces some kind of stream of encrypted data that's still compatible with whatever the packet producing layer needs, okay? So you have a lot of flexibility in there because the interface, that layer is only defined by its input and output formats. If there's some changes to that encryption algorithm, right, maybe you're shifting from 64 to 128 or 256-bit encryption, which is much stronger, you don't need to redesign any other part of the system. You could just focus in and say, yep, I can change that one layer. I know it's not going to have any impacts on the rest of the system because their interface, all those layers are defined by their interfaces. And if my layer is still producing output in a proper format, everything's going to be fine, right? Likewise, for physical media, before data gets transmitted out by your wireless card, ultimately it has to be converted into a bit stream, a series of ones and zeros. And so the layer above that is going to send that transmission, that bit stream conversion, some set of data, and that layer is going to convert it into a bit stream. And so whatever kind of data gets sent to layer 1, that's fine, it doesn't matter, as long as layer 1 can convert it into a bit stream, it's proper format, right? So if you change that transmission conversion and scheduling algorithm in layer 1 and try to say, you know what, we're going to adopt a different model for how often and when this thing is going to transmit, it's not going to affect what any of the other layers need to do. So again, you can change that transmission scheduling algorithm and it's not going to have big impacts on the rest of the stack, okay? That's why these layers are implemented in a modular way. Obviously, this is an example of a loosely coupled system, right? Same as we talked about before, the general properties of a loosely coupled system. You do take a performance hit. It can't push through quite as much data as it could if all these layers could freely share information, but it does make modification of those layers much, much easier. Okay, so for example, if all of this were just one single big layer from layer 1 to n, it was all just one box, you wouldn't know for sure that if you change something in the transmission scheduling algorithm, it might rely on some data from somewhere else in one of those layers, and you'd have to verify that nothing changed or was irrevocably damaged by that change to the transmission scheduling, okay? And you don't want to do that because that's a big headache. The performance hit is a relatively small concern compared to the problem of needing to consult your entire stack anytime you make a change to the system. Okay, now, packet shipping example. So all of this stuff for sending data over the internet, sending packets over the internet, is actually a lot like sending stuff through the mail. So, suppose you are sending a coffee mug to a buddy of yours in Australia. How would you go about setting that up? How would you, what are the ordinary everyday mail shipping tasks associated with sending a package? What would you do? Step 1, get a box. Yeah, then what? What's that? Wrap it up. Okay. Anything else? Go to the you're going to go to the post office with this blank box? Well, they don't know. Yeah, I mean, yeah, maybe, right? Or you just put the label on yourself. In most cases, I guess that's true, right? Like FedEx, if you have, well, you need something and they can slap a label on it. But let's say you put the label on it yourself. Okay? Sure. Okay, so you take the box there. The post office looks at it, sees it's labeled. What else do you have to do? There's a box, it's labeled. The post office person at the post office counter is kind of looking at you like, no, the thing's in the box already. You've wrapped it up. What's that? Why do you weigh the box? No, the shipping address is on the label. Why do you, that's all right. I talked to him, but why does the post office weigh your box? Because they're just kind of curious about how heavy it is? To know how much you got to pay for it, right? You got to pay the post office. Yeah. Okay. So let's say you've done that. You've achieved all these ordinary everyday post office tasks, and the post office has graciously agreed to take your package and put it in the mail system. Okay? So what happens? Do you think that the post office reserves a plane with a first class seat and gently puts that package in the first class seat on the plane to Australia? Did someone say yes? No, that's not what they do, is it? What does the post office do? What do you think they do? Do they have a straight flight to Australia? No. Yeah, they put it in some kind of shipping box, right? Some kind of cargo box, right? And they put it on a plane. And there's probably more than one cargo box on that plane, isn't there? Yeah? And the plane's probably not going nonstop to Australia. They're going to make some stops midway from Chicago, right? They're going to maybe stop in LA, and if there's a cargo box for LA, they're going to pull that. And then they're going to go on to Hawaii, and if there's a cargo box for Hawaii, they're going to pull that box. And finally, they get to Australia, and they're going to take your box that has, your package in it and dump it off in Australia somewhere and give it to the Australian postal system. So in this map, you take it to the shipping company loads it on a plane. At each stop, the plane parks for a second. Some guys come out, look at the box, and they say, oh, they eventually look at your box to Australia, the cargo container, and they say, nope, this is on the right plane. It's supposed to stop here, but this box is not for us. The box stays on the plane keeps going, right? They do that in LA, they do that in Hawaii. Eventually, at the end, they get to Australia, they look at the box, they say, hey, this box is for Australia. So they take the box, they open it up, they allocate all the packages to all the mail carriers nearby. One of them eventually gets your package and sends it onward to your friend's house, who's very happy to open the package and get the coffee mug. Okay? And this is, again, a lot like how data delivery actually works as far as sending it over the internet. All right. Now, every computer and network on the internet uses the same protocols to control transmission timing, data formatting, right? They're basically all using the same scheme. The dominant one being used is TCP/IP, transmission control protocol / internet protocol. Something like 95% of ordinary traffic. A few percent is something else called UDP that we'll talk about next lecture. The rest is basically diagnostic messages being sent by various devices on the internet to each other. Okay, so TCP/IP is the dominant model used, and TCP/IP basically covers most of the functions in the same sequence as the OSI model that we'll cover in a bit. But in general, it's more flexible than OSI. OSI is a pretty rigidly specified protocol for this. And big thing about TCP/IP, it doesn't specify the physical layer, the devices that actually transmit the data. So anyway, no matter what type of computer system you use to connect to the internet, if it uses TCP/IP, right, it's part of that standard way of doing things, it can communicate with any other device on the internet. Okay. Now the 4 layers of TCP/IP: application, transport, internet, and link. Okay. Application layer constructs the outgoing message. What is this? Yeah, with the destination address. Sorry, I was thinking like IP address. But basically, your application produces some data, and it says, all right, here's where this thing needs to go. Okay? The transport layer is basically responsible for chopping the data into packets and putting the things like the source and destination address and the packet sequence number on every packet. The internet layer is responsible for handling the routing. Now, of course, you're not going to handle all that routing on your own machine. At some point, you have to pass it off to another machine. But it's going to tell the other devices, it's going to figure out what the next device on the path is. So, for example, your local network, your device knows any devices it's directly connected to, including the router. So it's going to send the first message to the router, and the router will say, okay, yeah, I have this message. I don't know who I'm going to, send it to because that person isn't on my network. I'm going to have to bump it up to the local service provider. Local service provider may have to bump it up to the regional provider and him up to the backbone and so on. Okay, but the internet layer basically controls where the packets are getting sent to as far as when they're out of the system. It's like an addressing label. And the link layer handles the actual transmission of packets between machines. So the link layer is going to schedule when transmissions happen and take that packet data and convert it to a bit stream so that your wireless card can transmit it to the router. Okay, those are the basic 4 steps there. Now, as far as how this works, this is a similar thing. Notice the image is very, very similar, right? Not a coincidence. So the application layer prepares that message, gets it ready to send out. The transport layer chops it into packets. Network layer assigns the intermediate address to each packet, basically who is the next stop on the routing path. And then the link layer gets ready to transmit the message. So suppose you are sending this message out. Instead of a coffee cup going in the mail, you're sending an email to somebody in Australia. Well, what's going to happen is that message is first going to go to your router. The router will receive it as a direct communication at the link layer. The router will look at this message and say, is this for me? Am I the intended immediate recipient for this transmission? The answer will be yes. So because the router is supposed to handle the message, it passes it up to its own network layer or internet layer. Okay? When the network layer looks at it, it's going to ask, am I the final destination for this message? The answer will be no. You're not just sending an email to your router. So the router kicks it back down to the link layer to be retransmitted. And your router sends it to another router which does the same thing, and it sends it to another router which does the same thing. But eventually, it gets to the router that is at the other person's house, the recipient's house, right? And at that point, that router forwards it to, says, oh, I know where this recipient is. This recipient is on my network. That router transmits it directly to your recipient's machine. Its link layer looks at it, says, yep, I'm the intended next recipient of this message, kicks it up to the network layer. The network layer looks at the packet and says, oh, I'm the final destination for this packet. Great. So the network layer kicks that packet up to the transport layer. The transport layer adds it to the packet sequence that it's been getting for this message. When all the packets are in place at the transport layer can kick that information up to the application layer, and the person will get an email, right? So at every step along, every device is asking these questions. Is this message for me? If it is, I got to do something with it. If it's not, I'm going to ignore it. Now, in a lot of cases, it's pretty obvious that there's only going to be one recipient, one immediate next recipient for a message. But imagine that all of us have mobile phones, mobile devices, and I send out a transmission to somebody. All of your devices are going to hear it. They're all going to see that packet, right? But it's not going to be for any of you. So all of your devices, they're going to look and they'll say, oh, here's the source, here's the destination. I'm not involved with this. I'm going to ignore that packet, right? So in wireless communications, it becomes a very significant issue. Okay. It can also become a significant issue when you have a lot of devices directly connected to each other. So we'll bring up switching versus routing. So switching and routing are two different techniques for packet handling. Switching is for direct connections between devices, for example, within local area networks. So if you have all of the devices in your house somehow directly connected to your router, right? Those are switch connections. And the basic idea with a switch is that there's some kind of box. It can accept inputs from a bunch of different devices, and it can send them out as outputs to a bunch of different devices. So it kind of acts as a switchboard between all the different devices on your network. That's what a switch is. It's a hardware device. And then the core problem with switching is just anytime a device receives a packet, the sender might be connected to multiple devices, right? The signal might have gone on to multiple devices. So the recipient needs to look at it and say, am I an intended recipient for this message? Routing is for the connections between devices in different networks, okay? The core problem for routing is if there is a packet coming in, the question is, if it gets to routing, you've already figured out that you have to handle the packet in some way, right? It gets received at the link layer. You say, yeah, I got to do something with this packet. You kick it up to the network layer to figure out, am I the final stop for this packet, or do I need to send it back and figure out the next stop on the path and tell it where to go? Okay, so if the data link layer finds the packet is for me, am I its final destination? That's the question. Okay, so again, switching happens at the link layer or the data link layer in the OSI model. Routing happens at the internet layer or the network layer in the OSI model. Okay, now talking briefly about the OSI model, number one is a proposed standard from the 70s, is very useful for teaching, but never actually implemented anywhere. And it's a highly structured process, which in fact was its failing. It was actually too structured, and all the people involved couldn't figure out a way to make it work. They just had endless committee meetings and arguments, and they never really solved it while TCP was going out inventing the internet. Now, OSI has 7 different layers, and we're going to talk about what those are briefly. So, number 1, application. Number 2, presentation. Number 3, session. 4, transport. Number 5, network. Number 6, data link. And number 7, physical. And we're going to compare these to TCP/IP. Now in the OSI model, you have this. These 3 layers correspond to the application layer in TCP/IP. Okay, presentation layer is basically concerned with things like data compression and encryption and decompression and decryption. Session layer is for joining together traffic from related applications. For example, if you go to YouTube and you start watching a video, there's one stream for the video and one stream for the audio, and they need to be synchronized. The session layer also stores information about your session, the fact that you're connected to YouTube, and you might go from one page to another without having to log in again. Okay, so those 3 layers correspond to the application layer. The transport layer, pretty much same as TCP/IP. I mean, for all these things, there are differences, but for IDS 200, pretty much the same, okay? Pretty much same as TCP/IP network layer. Pretty much same as TCP/IP link layer. And no physical layer specified by TCP/IP. Okay? So we'll talk about this one for a minute. So that was freaky. Okay. So TCP/IP does not specify a physical layer. Reason is, if you think about how the layered system works, the data link layer is automatically going to send data in a format that's acceptable by some device, right? So one of the things the OSI guys wanted to do is they wanted to actually specify what the hardware that involved in networking would look like. And the TCP/IP guys, they were basically like, guys, this is 1970. Our networking stuff is basic. Of course it's going to get better and different, and we don't know what it's going to be like 10, 20, 30, 40 years on the road. But here's the thing. If we've specified the link layer and the data comes out in a standard format, then any hardware that accepts that standard format will be able to do the job, right? We really don't need to specify a physical layer. Well, with OSI, what happened is, you know, you had 2 big camps basically. One was the telecoms, and they really wanted to stick with the circuit switching model because number 1, it was easy to track usage, And number two, they weren't really interested in reducing costs for everybody. You know, they wanted people to pay for what they were trying to do. So the telecom guys, they were like, we really like circuit switching. We want to use this kind of hardware that supports that. The network guys, they say, you know what, we really want to use packet switching. We think it makes a lot more sense. It's going to be cheaper. It's going to make people happier. And we want to specify physical layer hardware that supports packet switching, right? And that was one of the big arguments that went on and on. It wasn't the only one, but it was a big one. Meanwhile, the TCP IP guys, they said, you know what? Why make you choose? You can use whatever you want. If there's some telecom that wants to rely just on, you know, circuit switching, great, they can try to do that. If there's another telecom out there that is willing to try packet switching because they think it'll make their users a lot happier, that's great, we can do that too, right? They're not going to force people to make that kind of choice. Anyway, and the way it eventually turned out is that while the OSI guys were spending decades, literally decades, in endless meetings just trying to decide what the internet would be, TCP was out there actually doing it. So here we are. Other thing in terms of flexibility, because I said TCP IP is more flexible, with OSI, every packet, every message is going to do that same series of steps, right? But a lot of messages aren't encrypted and don't need to be compressed, so they can totally skip that presentation option. Likewise, there's a lot of applications where the session layer information is maybe not that important. There's no session to manage and there are no related data streams to handle. So, you know, if it's not for a website that you actually have to log into, you don't really need to do the session stuff either, right? And for that matter, you might want to do encryption of the message after you do any of these session-related tasks. There's cases where you might want to do that. So TCP, by bundling those three sets of tasks into one single layer, allowed for a lot more flexibility than OSI had. All right. Now, quick recap, TCP IP versus OSI. Of course, TCP only has 4 layers, OSI has 7. We've talked about the correspondence. TCP IP's application layer encompasses those 3 from OSI. TCP's transport internet link layer, basically the same as the corresponding ones in OSI. But unlike OSI, TCP IP doesn't specify a physical layer, but only the formats of the inputs and outputs, which, if you consider how these layers work, that's enough, right? Any transmission, any kind of hardware, physical device hardware that can handle that format is going to be fine. And if you're interested, a very readable article about how OSI ended up not being the protocol of the internet. Okay. I'll mention this other last thing from Paint, and then we have a quick recap slide. So, if you're interested in these kind of things, quick mnemonic for OSI, all people seem to need delicious pizza, right? So there's that. I'm sure somebody can think of an ATIL for the other one. All teachers, yeah, I got nothing. I said I had nothing this morning and I have nothing this afternoon, but maybe you can think, I don't know. All teaching is lost, I guess. I don't know. Something. Anyway, here's the recap. So things you should know, because I know I tossed out a lot of information, but this is how it's going to go. We're going to have 1 lecture per session going forward till the end. So things you should know: what is the internet backbone? What are tier 1, 2, and 3 ISPs? What distinguishes them from each other? What are peering and transit agreements, right? These are things that will show up on the exam. Number 2, what are APIs? Why are they important to the internet? You know, what would the internet look like if it didn't use those APIs? What are routing, switching, and routing paths? So you should know what routing is, know what switching is, know what routing paths are, know what routing and switching are used. Routing is associated with the network layer, switching is associated with the link layer. And as far as the different layered protocols, what are layers? How are layers defined? Why are they separated? Why are they modular? All that. For TCP IP, know what the 4 layers are and what they do. For OSI, be aware of the 7 layers and what they do. And big picture, know the differences between OSI and TCP IP. Okay? That's all the stuff. All right. And it's been a hoot, and I will see you next time.